going on these noisy devices, and now we talk about working towards the NISQ photonics devices. Yeah.
Thank you, Dario, and I mean, thanks for the invitation to talk to you today. So I'm going to talk to you about NISQ photonic devices, but the most important word in this title is towards, because we're going towards them, but we're still very far from them, okay? And let's see if it works. I don't know. I think it's stuck. So different problems in different.
Yeah, today we are having uncommon problems.
Yeah, it works. All right. So it's essentially a talk about photonic quantum information processing, and I'm going to break down the words in this phrase for you. So the first part is photonic. So we want to work with photons, and more specifically, I want to work with single photons. And how do we get these single photons? So you can do it probabilistically, where you have a nonlinear medium and you impinge a pump laser and you get pairs of photons. You detect one, you know its twin is propagating, and you can use this heralded source of single photons. But you can also do it deterministically or semi-deterministically, where you you get your pump, you impinge your pump on a two-level system, like a quantum dot or a defect on a material, such as a 2D material or a silicon or diamonds, and then you get a photon out. Okay, and in this case, you can work at room temperature. In this case, you must work at low temperature if you want to get good photons out. So the next part is quantum information. How do we encode quantum information in this system? So the most naive way would be to encode it in the population of a waveguide, let's say. So if you have a photon propagating on the waveguide, you say it's in state 1. If you have no photons, it's state 0. But that's not good, because after propagating for a given length L, your one state would gain a phase while the 0 state would not. So it would mess up your quantum state. So what you do is that you do a dual rail encoding, so that if your photon is in the upper waveguide, you call it 0, logical 0. If your photon is in the lower waveguide, you call it logical 1. You're free to call it 1 and 0, whatever you want. But in this way, after the propagation, you get a global phase, so that it no longer messes up your quantum state, and so propagation doesn't disturb your state. But we want to do processing, so in a way we want to manipulate our qubits, but we want to do it deterministically, in the way we want, not just by propagating. And if you want to manipulate a single qubit, you can move it along the Bloch sphere by adding a phase to one of the waveguides, or by putting a beam splitter between the waveguides. Okay, so this implements a rotation along the z-axis, and this one, oops, now it decided to pass when I didn't want. And I'm pushing the wrong button. And this one implements a rotation around the x-axis. So if you start with 0, you apply a rotation around the x-axis, you take it off axis, and then you can rotate it like this by applying a phase, okay? So that's the kind of manipulation you can do. But we want 2 qubit gates. It's not that we want 2 qubit gates, it's that we need 2 qubit gates. If you want to do universal quantum computation, you need at least one 2 qubit gate. This was shown in the 90s, okay? So the idea is to do the controlled NOT gate. The controlled NOT gate, it operates like this. And it's important to us because it allows you to generate entanglement. So you can start with a separable state, and you apply a CNOT gate between 2 qubits, and you get an entangled state. Okay, you apply a Hadamard first, but anyways. So you see, you can start with this separable state, and you end up with an entangled state. So that's the way you generate entanglement. And it's relatively simple to implement in some quantum computing hardware, but not with photonics, because photons don't interact. And the best we can do is do Hongo-Mandel interference. So you are stuck with probabilistic gates. And this was somewhat depressing state of photonic quantum information processing until New, Laflamme, and Milburn, they've shown that it's possible to get this probabilistic gate to operate with a higher and higher rate of success, provided that you add more and more resources. So there is no free lunch. So you start with this nonlinear sine gate, so that if you have one photon, it does nothing. If you have two photons coming in here, it applies a phase shift to one of the photons. It needs an auxiliary photon, so I'm not going into the details. You can read it here. It's not an easy paper to read. It will take you a few weeks, maybe more. The notation is a bit confusing also. But if you want, I can point you to Luis's undergrad text on basically understanding what these guys are proposing. But this is what the CNOT looks like, okay? And it's heralded, you know when it works. And this is important, because then you can put the CNOT gate inside a more complex, so the CNOT gate is here, and this part will do a quantum teleportation. The CNOT gate fails a lot of the time. It only works 1 out of 16 times, but you know when it works. And when it works, you can trigger the quantum teleportation and you can teleport the correct output out. Okay, so that's the basic idea. It can get more complicated. If you want to see a more simple proof of principle thing to do not many CNOT gates, you can do this interferometer. They are all interferometers because, again, this is all we can do, right? We can only get photons together at beam splitters and see quantum interference. If you're working with purely linear optics. If you have a highly nonlinear element, then you can do more interesting stuff, but I'm not going into this today. But the thing is, while it doesn't need external resources, it's stuck at a probability of 1 out of 9 times of giving you the correct answer. You know if it works, you know if it doesn't work, but it doesn't scale. So if it's 1 out of 9, if you need thousands or even hundreds of CNOTs in your circuit, you're done. It's never going to work. So now is a good point to define what I mean when I'm saying photonic quantum information processing. In this talk, because it can mean many things. I could be talking about discrete or continuous variables. I could be talking about gate-based processing, measurement-based processing, or fusion-based processing, which is kind of measurement-based but a bit different. And for this talk, I'm talking about discrete variable, path-encoded, gate-based photonic quantum information processing. Because in discrete variables, I could be encoding my qubits in polarization, for instance. You can do this if you're working, for instance, in free space implementations. But so this is what I mean. So keep this in mind for the rest of the talk. If you want to discuss continuous variables, Felipe Barbosa is here, and he's the guy to talk to. So now we need a linear optical quantum processor, okay? And it was shown in 1994 that you can do this with an array of beam splitters. And it's interesting that they say that it implements any n by n unitary matrix, so this is probably a good thing for Diogo, provided that you have a suitable beam splitter. And this is 1994, and by a suitable beam splitter, they mean that you're friends with someone that can fabricate a small glass cube with the proper transmission and reflection coefficients. This is what they mean. And if you want to build, so you would need a whole bunch of different cubes to build your different unitaries. It's really not practical at all. But then we go to integrated devices. And so the idea here is to use the waveguides that I've already told you about. And the idea is that you have the electrical field confined inside a higher refractive index material surrounded by a lower refractive index material. If you bring two waveguides together, then you can have combined modes or superpositions of modes that become a super mode. You can have symmetric and anti-symmetric modes. And as these propagate, they propagate with different velocities. And in effect, what you have is this. You have an integrated beam splitter. And so this, you now only need to be friends with someone that can fabricate this for you. But there is an extra step, right? You can add phase shifters. We are now working with thermal optical phase shifters. This is a photo of a chip that we had fabricated in Switzerland. And these golden strips, they are resistors that will heat up the material underneath them and then change the refractive index, and you introduce a phase for the propagation along that waveguide, that section of the waveguide. But we want to take a step further and move on from thermal optical modulators and go to electro-optical modulators. And for this, we need to be able to, by applying a voltage, change the refractive index of the material. There are some platforms to do that. But then there is another interesting step, which is the fact that you don't need those purposefully made beam splitters to make your N by N unitary. You can have a programmable beam splitter. This is a programmable beam splitter. It's a Mach-Zehnder interferometer, so you need two fixed beam splitters. And then by adjusting these two phases, you can implement, it can be an effective beam splitter with whatever ratios of transmission and reflectivity that you want. Okay? It's also called Givens rotation. And it's known that with this element, you can decompose unitary matrices. You can decompose unitary matrices in a series of Givens rotations. Yes, so that's yeah, we'll maybe get to that later, yeah. But this is actually, so what I'm talking about here in terms of unitary, because I said I cannot do a deterministic C-naught gate, and that's true. So these unitaries, they are operating actually on bosonic modes, okay? And you can think of it as operating on a very large Q-dit, which is the D-dimensional version of the Q-bit. The Q-bit has two dimensions or two ports, and then with D ports, you get a Q-dit, okay? And in principle, you could do everything with Q-dits. The problem is the number of ports you need grows exponentially, so doesn't solve anything. So still, we can do a lot with this, but not everything. And so this is just the recipe to decompose a unitary in terms of these Givens rotations, or in terms of how do you program your circuit. And so George Sebenko gave an idea of this in 2001, and Clements and others gave also, I mean, so this is purely theoretical, and this is applied to programmable beam splitters. And this is a very widely used architecture for programmable photonic circuits nowadays. So how does the circuit look like? It looks like this. So it's a concatenation of Mach-Zehnder interferometers with some extra phase shifters in the end. So the number of Mach-Zehnder interferometers scales like this, which is essentially quadratically, and also, so the number of phase shifters scales as n square. So okay, it's polynomial scaling. It's not so bad. But even when we say it's not so bad, still having to deal with thousands of phases is still complicated from the engineering point of view. We have to remember this. Just because it scales polynomially, it doesn't mean that it's easy to implement. So essentially what we have is a circuit that will implement the gates. you can have a fixed set of gates for a given algorithm, but you can reprogram to implement different gates. So in principle, you could have implement different algorithms. And this is essentially different from if any of you have seen something about how superconducting quantum computers based on superconducting qubits work. Their qubits are sitting around in the processor, and they apply the gates as a series of radio frequency pulses. Here, it's the other way around. Our gates are sitting there on the chip, and we fly our qubits through the gates. Okay, so it's the opposite. And, well, while we don't suffer so much from noise as the superconducting qubits, we have the problem of not being able to do deterministic 2-qubit gates. And we also have the problem that, I mean, we have the advantage that the time for your qubits to propagate through the circuit is very, very short compared to the time it takes to apply a sequence of RF pulses, which can take microseconds each, so compared to picoseconds of propagation time here. But then we are probabilistic, so we have to do it many times. So in the end, I mean, you have to really do the calculation to see if it doesn't end up evening out. And so in the beginning, I talked about NISQ devices. Diogo talked about NISQ devices before me. So you already have more or less an idea. Thank you, Diogo, for presenting the idea first. It's a term that was coined by Praskil in 2018, and he wanted to talk about this kind of system that is big enough to be unfeasible to realize in a classical computer, but still not big enough to, you know, solve all the promising problems that we want to solve with quantum computing. And to give you an idea, so he puts NISQ in the range of 50 to 100 qubits. And so this is just to give you an idea of the size, the memory size you need to write down, to store the data for a 50 or 100 qubit state, a generic arbitrary state. Okay, for some states, it's easy. If it's just the vacuum, it's very easy. You can write it down on a piece of paper. But if it's an arbitrary state where you need to take into account all the coefficients, then it quickly becomes a mess. And for 56 qubits, it's more or less the limit you can store in the Summit supercomputer of the Oak Ridge National Laboratory, which is one of the largest in the world. So they're strongly limited by noise. In our case, the worst noise you can get is qubit deletion. So your qubit is absorbed, because it's a photon, is absorbed by the material, it's scattered out of the chip, it's not detected by your detector, you lost your qubit, and you have to start over again. But at least when we don't see the photon that was supposed to be there, at least we know that the computation failed and we need to run again. So it's a very detectable error in a way. And what I mean when I say that the more ambitious goals of quantum computing are still out of reach is that for you to simulate this molecular complex, which is the one responsible for fixating nitrogen in plants, we would still need thousands of qubits and billions of T-gates. So, yeah, it's, let's say, some years away, even for the best computers. Because remember, if you want to do this and get a proper answer out of it, you need these not to be physical qubits, you need them to be logical qubits. And the difference is that the logical qubits are error-corrected, and otherwise you just get noise, right? So you need thousands of logical qubits, and for some implementations, logical qubits will require many, maybe hundreds of physical qubits. So these things blow up, and it's very unlikely that we will one day have, you know, a personal quantum computer at home, unless you have a very big home. So why do this? Why work with NISQ? Because it's not so useful as we might hope, but it's very hard. And actually, that's more or less the point, that it makes you think about engineering constraints. It makes you think about what should you develop really to move forward the technology. And also, it helps you to establish this, which is very important, which is a reference frame to discuss between groups doing theory and groups doing experiments. So as Diogo presents things that he wants to do with NISQ, I can now present him my hardware and see, how can we do variational quantum computing or optimization, solve optimization problems with a photonic hardware. And then we can start to have this talk. And when we do this, we move the wheel, and then we think of new hardware to develop. And this goes back to talking to engineers about what are the constraints, what we can do. So this is just to give you an idea of what would be required to go to NISQ, to the edge of NISQ with photonic platform. It would not be so big, right? It's still manageable in terms of size, but it would require thousands of beam splitters, which would mean the order of 10,000 individual phases that would be precisely controlled. And this starts to become an engineering problem, because now you need hardware with 10,000 outputs that will control 10,000 independent currents, and you need to wire bond 20,000 individual gold pads to contacts and so on. So, and I mean, when you draw it on the board, it seems easy, but to make it become hardware, usable hardware, it's a challenge. And so this is why we need more contact with engineers, because sometimes they have the solution. If we approach the problem from the physics, from a physicist mindset, we can come up with very unoptimized, very brute force solutions sometimes. And then you talk to an engineer and they will say, but look, this is not how you do things. there is, a better way to do it. But there are bottlenecks, and the bottlenecks are more complicated to solve, and this is where really heavy research needs to go. And the first bottleneck is that if you want 50 qubits, you need to generate at least 50 indistinguishable photons. Okay. The best commercial single photon sources that you can buy nowadays can give you 12. They're promising 25 in the next year. Still, you need a long way to go, because you cannot buy 2 of these and say, now I have 50 photons, because photons from source A are not indistinguishable from photons from source B, because they use quantum dots, and quantum dots, they grow spontaneously. If you want to know more about quantum dots, talk to that guy in a white shirt, Dr. Simon Kovri. He's the specialist in growing quantum dots, actually, and telling you all, how it's hard to get them properly, how they will emit each one at a given different energy. If you want to make them, what they do to make them indistinguishable is that they use a single quantum dot to emit all the photons. So it emits a train of photons, and they demultiplex it from time to space, and you get every 25 photons that were emitted, you get 25 simultaneously, and then the next 25, the next 25 injection, and so on. But this is not very practical. So one thing that really motivates me in terms of research is to get multiple sources to become indistinguishable and for them to be put on chip, because then you don't need a huge platform. You can have something, the sources on chip and mutually indistinguishable. This is absolutely something we must attack if we want to move on to larger devices, okay? And we must invest in making better CNOT gates. Either that, or you give up on gate-based computing and you move on to measurement-based or fusion-based computing. It's There's nothing wrong with that, but it has its own set of problems, okay? That's something that you, as students, must remember. The problems are more or less conserved. If you move from, you look at the neighbor's platform, it seems better, it seems easier. When you get there, they have their own problems, which are as hard as yours, okay? So there is this. So what are we doing? So recently, Kalebi, he finished his master's, and we studied new ways to integrate these sources of light into the waveguides, okay? And, well, his main result was to find out that you can actually get very, very high coupling, over 90% coupling sometimes, or I mean, certainly over 80 here, of light emitted from a 2D material, for instance, a dipole, or it could even be a quantum dot, into this photonic structure, okay? And not just that, but we found that this specific structure also gives you a very high per cell factor, above 10, okay? So, which is comparable to the optical cavities that people use in that commercial single photon source. Maybe even better, could be. And this is important because the per cell factor gives you by how much the emission is accelerated by the fact that the electromagnetic field modes are structured by this dielectric structure that you have. So all of this to say, the faster you get your photons out of the solid state emitter, the better, because the less noise you'll have in the photons and the more they are indistinguishable and pure. So this is what it looks like when you transfer 2D materials to waveguides. And also we've been transferring them to nanopillars because when you do this, you can stimulate single photon emission from these 2D materials. So we want to be able to stimulate the materials to emit a single photon instead of having a gas of excitons, which are electron hole quasi-particles. And so you see, we're developing the steps to make this technology. We do it with this machine, which we built. It's color-coded for your convenience. You can read about it maybe later. And moving on, so what we also did was, Luis, who is also in the audience, his problem during his master's was, how do we take this Mach-Zehnder array and do something with it? And in particular, do something that is not just apply a big unitary. So we wanted to see if we could do, for instance, it was simulated, but it was to simulate doing a contextuality and non-locality experiment fully on chip. Can we do this with this kind of programmable chips? And the answer is yes. So first thing, he showed that with this design, you can use it not only as an 8x8 matrix, but also smaller matrices, and you can work like 2 qubits and 1 qubit. But in this picture, you are still applying only one operation per chip, and these chips are expensive. So you want to use them at their full capacity as much as possible. So his idea, and I mean his and Maria Carolina and also Otavio, who at the time was working at our lab, they were discussing one day and they came out with this idea that if you put extra phase shifters here, then it can be block reconfigured. And actually, if I remember correctly, they came up with this idea in part because during our meetings, I would always, you know, draw these blocks in the chip and say, so this can be, you know, a 2-qubit operation, and this can be a C0 and whatever. And one day they looked at it and said, no, but that's wrong. You cannot do this with the regular chip. And then they came up with a way to do it, actually. It was a very clever idea. So you see, now you can break down your chip into programmable parts, which will then implement a Bell test. It can implement a contextuality test, and it can even implement a joint contextuality Bell test. Well, the Bell state preparation is is not here because it doesn't fit, but if you have a larger chip, it can fit. So there's nothing in principle preventing you from using this architecture to program gates into your chip, which is exactly what we want, right? But to do all this, we need to develop a classical controller. We are doing this. We have a project. It's funded by CNPq, and it's to make this classical hardware. It needs input, which is photodetectors. It needs a controller, which is an FPGA chip. It's a kind of programmable controller chip. And at the output, you need digital analog converters to take out the information that was processed and turn it into either currents or voltages that will be driven into your circuit. This is all being done by engineers. Okay, so again, we need to talk to engineers to help us solve our technology problems. And in the way, during the process of doing this, they also, learn about quantum information processing. So it's interesting for both parts. This is what the chips look like. I highlighted some parts of the chip. Everything is here. So this is a single Mach sender. We planned it to have dual input just because we could, this is a playground chip. It's not intended to be, let's say, the final version. But we wanted to test some ideas. And we also did this, which was for another group, a group from Belo Horizonte. They had this theoretical paper on a circuit that could do quantum state tomography, optimized. So instead of using a programmable chip, doing something else, and doing quantum state tomography on a qubit, a state with three levels, right? So 0, 1, and 2. So we designed this for them, right? So this is a qubit state preparation stage, and this is the qubit tomography stage, okay, which was built according to their designs. And now we started testing this. We haven't heard from them in a while. I'm curious if they already did something with it. But anyways, this is what the chip actually looks like. Unfortunately, we don't have much of an intuitive scale, but this is a screw head, which is like this big. The chip is 1 centimeter, okay? So you can more or less use the chip as a scale bar. It's 1 centimeter long. So this is what it looks like when you access it with a fiber input and a fiber output. Okay, so just one input, one output for the first tests. Later, you want to come with fiber arrays and couple these fiber arrays to your chip, and maybe do it permanently. So this is what's called packaging the chip. The electrical connections here have not been made yet. You have the electrical, the contact pads on the chip, but we still need to wire bond everything in order to drive the heaters and implement whatever we want to implement. In the case of this chip, which is the one for tomography, we only really needed to fine-tune a bit the beam splitters and to do the quantum state preparation stage. So these are just pretty pictures of light propagating on the chip. You can see the light because it's scattering out of the chip, which is not what you want. But then again, this is not the wavelength it was designed to operate on. So, okay. And so in this way, you see that at least light is coming in. And it's funny because we borrowed this, Maria Carolina, she borrowed this supercontinuum laser from Gustavo's lab. And you can see that different colors come out of different outputs. And this is because this kind of device is very dispersive. And so it will behave differently for different wavelengths. So in a way, it's kind of a diffraction grating. It's separating the wavelength in the output. But this is not, let's say, something we intended in the beginning. And then Maria's work, one of the things she did in her master's, she also worked with 2D materials that can have applications for machine learning, and so optimization also something we could discuss. But one of the questions she worked on during her master's was this, which is how much energy does it take for you to actually program this photonic processor? Because at the end of the day, you need to plug it into a power outlet and program it. So we set up this question thinking of, state-of-the-art electro-optical modulators. So they use much less energy than heaters. And we defined a task to be performed by this hardware, which was arbitrary quantum state preparation, which is one of the stages of the variational algorithms that you saw earlier. And the thing we found out is that it actually takes a lot of energy, and it can take more energy for you to do it with qubits than with qubits, which was a bit surprising, actually. Because usually you have this idea that since qubits blow up exponentially and qubits do not, qubits would always be more efficient, but that's not true. And that's not true in large part because of the task we are performing, which is arbitrary quantum state preparation, and which is known to blow up exponentially in the number of CNOT gates you need to apply. So you need an exponential number of CNOT gates, and CNOT gates are expensive to program in that generic framework that I've shown you. So in summary, I mean, this is a speech that gets quoted a lot. People usually like just to put the not because they're easy, but because they're hard part. But what interests me most is what comes afterwards. Because, I mean, the first part is a bit weird by itself, right? But, I mean, Kennedy was talking about doing, these very hard things, fly the Atlantic, Rice playing Texas. I assume one of them is really bad at football, American football, or climbing the highest mountain. And so, but this is important, right? It's a goal that serves to organize and measure the best of our energy and skills. So it's really a test of how far can we go? What's the best technology that we can sit down and develop here at Unicamp and collaborating with colleagues in Brazil? How far can we go with this? It's a very hard goal, to try to scale up to this, but it's worth it, and we learn a lot along the way. So just to acknowledge some funding I've had, CAPES is here because I spent 3 months lately in the US funded by CAPES. Part of this work was funded by the US Air Force. Part of it was funded by the National Institute of Science and Technology for Quantum Information, and also CNPq and FAPESP. And today we came, with the help of our institute here. Thank you. See, photons have less noise.